Good. All right, hey everyone. Welcome to the second DataFusion San Francisco meetup. My name is Matt, and I am one of the organizers here. So thanks for everyone coming out on a Wednesday. We've got some good speakers lined up for you today. And so I guess without further ado, we can just jump right into it. So coming up to the stage first is going to be Micah from Arroyo Systems.
Thanks, Matt. Excited to be here. Let me just figure out the slide situation. It's loading. Very exciting. Yes, I have typed it in, and now it's still loading. Oh, very cool. Okay, cool. Hey everyone, thanks for coming out. Excited to be here on the second San Francisco DataFusion meetup. Today, I am going to be talking about how we do dynamically loaded user-defined functions in Arroyo. So before we dive into that, a little bit about what is Arroyo. Arroyo is a new SQL-based stream processing engine. It's built on top of Arrow and DataFusion. It allows you to do stateful computations like windows, aggregates, joins, etc., on top of streams of data with full consistency and fault tolerance. So if it crashes, you can recover without losing data or double counting events. It's built from the ground up for modern cloud environments. So it's very good at scaling, scaling down when you have a few events, scaling up when you have lots of events, dealing with node replacement, stuff like that. And it's also designed to scale down to really small scales for people who don't have a lot of data and want to run this on like a serverless platform, for example, and scaling up in a distributed horizontal way to millions of events per second. So I'm going to be talking about user-defined functions. First, why do we want user-defined functions? And the answer is that, well, SQL is a very powerful language. It usually comes with a lot of like built-in functions. It has a lot of ways to like combine them in interesting ways. But sometimes you need a little bit more. You need like a real programming language. Maybe you need to like parse an internal binary format, or reuse some existing business logic, or implement a custom aggregation, or call some external service, perform an ad hoc join. Or a little bit closer to home, sometimes you may need to work around missing features in like a new engine written by a very small team that hasn't built everything people might need. So being able to like provide extension capabilities is a really powerful tool, when you're building a new system, to allow people to like solve their problems, even if you don't necessarily solve it for them. So UDFs in DataFusion. DataFusion actually has support for UDFs out of the box. They provide this trait called scalar UDF impl, which you basically fill out these things. You give it a name, you give it a signature, to how to what types it can be called on, what arity of arguments. Give it a data type, and then implements invoke method, which actually runs the UDF. And this is pretty powerful. So here's an example UDF implemented with this that implements the toHex SQL function. It converts a number to a string hex representation. You can kind of see what this looks like. And something really cool is that actually, as of recent releases of DataFusion, basically every function is now implemented as a UDF. What that means is that the UDF system has basically as much power as the engine needs in order to implement all SQL UDFs, which is super cool and a really great achievement by the team working on DataFusion. So maybe the answer, if we have an engine and we just want to provide UDF capabilities to our user, maybe we can just expose the DataFusion UDF API directly. but there's a couple problems there. First problem, that API is actually pretty complex if we want users to actually implement it. They need to understand a lot about kind of the internals. They need to be able to use the ArrowRS APIs, which if you have worked with them is not a straightforward thing. They need to deal with like polymorphic SQL type signatures. So SQL functions can take various types of arguments with various arity and data types. They have to be able to deal with nullability, which is a really, really complex topic in SQL. They have to implement that DataFusion UDF interface, and they have to be able to deal with the fact that their arguments may be either scalars or arrays. So it's just a lot for like an ordinary user who just wants to do something to kind of think about. So looking back at that like 2-hex function, like, there's a lot of complexity here that's not really related to the problem that they're actually trying to solve. If you look at like the actual implementation of the 2-hex, like again, there's just like a lot of code for something that's pretty simple. Like a user ideally just wants to write this. Like they just want to implement their business logic and not think about how do we convert all these different arrow types into like a Rust type? How do we produce our result into an arrow array? They just want to implement, whatever they care about. The second problem with just exposing the DataFusion UDF API is that UDFs need to be statically compiled with your engine. And to ground this a little bit, like this is kind of the experience we want to provide. So this is the Arroyo UI. We want to have like a web UI or an API where users can just provide UDF code, and we're kind of able to like, compile it for them, distribute it to the workers, like execute them, and we don't want that to like be a really expensive, complex process. If we wanted to just use like the DataFusion UDF API, we'd have to ship Rust C. We'd have to wait for an entire engine to be recompiled with the UDFs for every query, which for our engine, a full release build takes like 15 minutes on a fairly powerful machine. So that's a long time to wait to run a query. If you want to mitigate that, you have to ship like a really complex like caching infrastructure. We used to do all that, by the way. The previous version of Arroyo was fully ahead of time compiled, so we would like generate Rust code for all the queries. But now we use DataFusion, and it's great. Everything's dynamic. We don't have to do all that, and we don't want to like reintroduce that just to support UDFs. Okay, so we want to build a easy-to-use dynamic UDF system. So how do we do that? Well, we have a few different options, and if you kind of survey the landscape, there's like different ways this problem is solved. The first answer is to embed a dynamic scripting language. So this is great because dynamic languages don't need to be compiled. They don't need to be built in to the engine. So for example, we can like embed a Python interpreter. People can just give us Python code, and we can just execute that as part of the UDF. And in fact, we do this now in our latest release, which came out yesterday, 0.12. We do now ship Python UDF support. But unfortunately, Python is really slow. So if you want something like native performance, you really need to look elsewhere. The second option is to run our UDFs in a separate container and make RPC calls to them. It's another common solution to this problem. The advantage is we can just compile the UDF into its own service. We don't need to compile it with the whole engine. The downside is that, again, it's really slow. There's going to be a ton of serialization and network overhead, and we have to copy the data a bunch of times. And we're just not going to be able to hit that like native performance that we're really aiming for. On the other hand, this can be great, especially if you're running like a managed platform. You might want like the isolation and security and sandboxing that a container gives you, but it's not quite the solution we're looking for. Third option, which is increasingly popular, is to use WASM. So we can compile our Rust code to WASM. Now this is the thing we can dynamically load and execute, and we don't need to do this expensive static compilation process. And again, this is a great option for a lot of systems. It gives you sandboxing, gives you isolation. The performance is pretty close to native, often like 70% or 80%. I would say the biggest downside today, besides like the little bit of performance overhead, is that not everything can be straightforwardly compiled to WASM. There's a lot of edge cases, and your users have to be aware, like, okay, how do I make this library I want to use like WASM compatible? So the fourth option is to dynamically link a static library. So we're going to compile the UDF to a shared library. We're going to compile the UDF to a shared library, like a .so on Linux or a dylib on macOS. And then we're going to dynamically link that with the engine so that we don't have to compile it all ahead of time together. And, surprise, surprise, this is what we ended up doing in Arroyo. So, okay, let's do some dynamic linking. Unfortunately, if you try to do this in Rust, you very quickly run into a very large problem, which is that Rust does not have a stable ABI. So an ABI, for those who aren't familiar, is an application binary interface. This is basically the standard that says how your data types are laid out, how much space they take, how they're ordered, and what your calling convention is, what data you pass in registers, what data you pass on the stack. And the Rust compiler today is free to just decide whatever it wants to do because it assumes everything's statically compiled. As long as it makes one decision at compile time, everything will work out. But if you upgrade your Rust compiler or use different compiler flags, you may end up with a totally different struct layout, and you can't dynamically link those things together in a way that's going to work. So the workaround here that we use, and is sort of the standard answer here, is surprising for Rust programmers. We are going to use some C, or specifically the C ABI, which is as close to a standard as we have in systems. It's for every platform and architecture, there is a standard calling convention that C uses. There's a standard way to lay out data. And so it's become sort of a lingua franca in these system spaces. We always can rely on the C ABI. So here's sort of what we're going to do. We have some user code in the middle here, the kind of raw Rust function that the user wrote. We're going to wrap that in a C ABI compatible interface that knows how to do the conversion from arrow types. It knows how to expose this as a C library. And then in the host, we're going to implement the scalar UDF impl that's going to call that C compatible interface. Actually doing this is, again, fairly complicated. There's a bunch of rules we have to follow in order to get C compatibility. So one rule is that all of the data must have this repr_c annotation. The reason for this is that, again, Rust doesn't define any standard layout for your data. So if we look at this struct, for example, Rust is going to lay it out in this way. It's going to, you may notice, actually reorder the fields. So we said A, B, C, but here it's B, A, C. The reason it does that is that everything has to be aligned to 8 bytes. And by reordering the fields, it actually reduces the amount of space that this takes because it's able to basically save some aligning bytes. If we mark this repr_c, then this gets laid out in the same way that C lays it out, which is always in the same order that you define it. But you see here, because we have this this F32 that takes 4 bytes, it has to now pad it by 4 bytes to get that 8-byte alignment. And so we end up using way more space, 24 bytes instead of 16 bytes. So it's cool that Rust does this for us, but again, it causes problems when we're trying to be compatible across things that are compiled by different systems. The second rule, which is very limiting, is that all data must be FFI safe, which means basically you're limited to the things that I've listed here. I'm not going to go through all this, but basically you can use primitive types, you can use raw pointers, and you can use structs and enums that are annotated repr_c and only contain fields that are also in this list. So pretty limiting if you're used to the rich diversity of normal Rust types. Functions have to be marked as no mingle, which basically tells the compiler not to change the name. Normally, it's going to generate some name for them so that there's no risk of duplication. And then also extern C, which just tells it to export it as part of a C library. And then the last rule, you cannot panic. Panicking is not safe across a FFI boundary. It is undefined behavior. It, at best, will cause segfaults. So with all that, here's kind of the steps you follow to build a plugin system in Rust. We're first going to define our data types as FFI compatible types. Then we're going to define an interface with extern C functions. We're going to compile our plugin with this special crate type cdylib, which tells the compiler to produce a C-compatible dynamic library. And then after we have that dynamic library, we're going to load it from our host. There's a few different libraries for this. We use the dlopen2 crate. So that's all kind of the background. Here's how this actually works in Arroyo. This is our plugin interface, at least for kind of the simplest case of synchronous scalar UDFs. We have a single function we export, which is called run. We kind of underscore it a few times to reduce the chance of running into any other symbols that the user might define. This takes some what we call FFI arrays as an argument and produces a run result. If you look at those types, remember again, everything has to be FFI compatible. Fortunately, ArrowRS already provides FFI compatible versions of arrow array and arrow schema, so that saves us a lot of work. But we need to kind of wrap that in some structs so we can package them together. And then we can't send vec across an FFI boundary because that's a Rust type. It's not repr-C. So we have to like decompose it into its constituent parts in order to send this. And that's what that looks like. And then again, we can't send result because it's not FFI safe. So we define our own result that is repr-C. On the host side, basically, we take in the columnar values, which is the arguments to a UDF, and we decompose it into these FFI safe types. And something to note here is there's no copying involved. There's no real overhead. It's just kind of telling the compiler that like, oh, this thing you think is this thing, it's actually this thing, but it's not actually changing the data. And because that is not something that Rust can prove, there's unsafe involved here. Anytime we're going across a C boundary, the compiler can't really prove anything about that, so everything is unsafe. And then we actually call our UDF and then manage the result. But the end result of all this is that our users get this really nice UDF interface. They don't have to think about Arrow. They don't have to think about DataFusion. They don't have to think about C FFI compatibility. They just write their function that does their thing with normal Rust types, and it all just kind of gets handled for them. The magic for how that actually works is here. It's this UDF macro. That macro is doing a bunch of things that make this all work kind of behind the scenes. It parses the type signature, so it figures out what's the name of the function, so that's how you're going to call it in SQL. It figures out what the arguments are, what the types, and the return type. It figures out what the nullability behavior of this function is based on whether things are marked as optional or not. So if it's optional, we're going to call it with all of our data. If it's not optional, we're only going to call it on the non-null data. And then it generates a bunch of wrapper code that implements that FFI conversion, iterates through each array and calls the function, builds up the result array, and then wraps everything in standard panic catch and wind, which ensures that no panics can cross that FFI boundary and cause potentially seg faults. If you want to see what that generated code looks like, it looks like this for that example function. It's a little bit reduced to fit on the slide, but it's basically sort of what you would expect. Something very cool here is that this actually gets optimized to something that's basically the same as what would happen with a normal DataFusion UDF or function. So this is essentially native performance for like the things that are actually part of DataFusion. There's a little bit of optimization capabilities because it's across the FFI boundary, but generally you should expect native performance from this. So I want to do a little demo of this. We'll see if this actually works. Always risky. Cool. So I'm going to just start Arroyo here on my laptop. I already have this running somewhere. Okay. I'm going to start Arroyo on my laptop. And one cool thing about Arroyo is that it does ship as a single binary. That's one of the things we get from all this work that I'm talking about. And so I can just install it with Homebrew on my laptop and run it. I'm going to pull up the web UI here. And I'm going to create a pipeline. I already have actually the code here, so I don't have to type it. But yeah, so one thing I mentioned people like to do with UDFs is to implement like custom parsers You may have some like custom binary format or other format that we don't ship a parser for. One common format people deal with in this space is called common log. It was originally like the Apache web server log format, but now it's been kind of widely adopted. If you're dealing with web logs, you probably have to deal with this. And we don't ship a parser for it, obviously, because it's pretty specialized. But it's easy to pull in some libraries and do this in a UDF. That's what the UDF looks like. We allow you to specify dependencies that we're going to use to compile this, and then you annotate the UDF with the UDF annotation, take in your arguments, produce your result. Here we're producing an option string because this may fail, and if so, we'll just produce a null. And then we're basically just parsing out the fields and producing this as JSON so we can consume it later. In the query, we're basically, I have like a demo generator source running locally. So we're just going to pull from that, and we're parsing the value here with this parse log function that we just defined. And we support like virtual fields, so you can kind of stick this in the actual source schema, which is kind of convenient. And then we're able to just pull this out and hit preview. Behind the scenes, it's going to compile that UDF into a shared library and execute it for every record that comes in. This is what it looks like. We can use JSON functions to like pull out the thing we're particularly interested in, like maybe the host. And yeah, that all works. We could, group by the host and count and see, if it was malicious or whatever. But yeah, so all of that actually works. Cool. So what's happening behind the scenes here? We have that web UI. When you hit preview, it's making a request to the API server that I'm also running on my laptop. It's sending the UDF code, which then gets sent to another compiler service. In this case, it's all kind of running together, but you could also run this distributed if you wanted to. The compiler service generates a crate for that UDF with all of the dependencies that we specified. And then it compiles that as a C DYLib, either a .so on Linux or a DYLib on Mac. And then it writes that to some storage. Typically that's S3, but in this case, just my local file system. And then when the workers run, actually executing that query, they're going to download that .so file and load it and call it when that UDF appears in the query. So this is kind of like the basic case of like what we call scalar synchronous UDFs. So these are UDFs that are expected to run very quickly and operate on a single value. We also support some kind of like more advanced UDFs that I don't really have time to get into detail, but happy to like chat with folks about how we do this later. One of those is what we call async UDFs. So these are UDFs that can use Rust async functions. And that's quite powerful for a lot of things people end up wanting to do to extend kind of like, I would say, limitations in the engine. Things like they want to query an external service. They want to do some kind of like ad hoc join. Like maybe they have a database that has fact table data that they want to join with their streaming data. They can do this with an async UDF. Maybe they want to like call out to an ML inference model. I have to say something about AI. I think it's the rule. And the way we implement this is quite complex. You can't share. So Tokyo, for those who don't know, is like the standard Rust async runtime. It's what DataFusion uses for all of its lightweight threading. Unfortunately, you can't share Tokyo across an FFI boundary for a bunch of reasons. So we actually have to run a separate Tokyo reactor within each UDF kind of like FFI space. And that kind of maintains its own queue that gets data from the host and produces kind of the outputs and then returns them. We also have to implement our own async UDF operator rather than using kind of the built-in UDF system, because these things may take a long time to run, and you really want to run them in parallel. In order to do that, we need our own operator, so we can basically parallelize them and re-aggregate the results as they return. Something else we support is UDAFs, which are aggregate functions. These are things like count or average. We allow users to define their own versions of these. Currently, we only support a fairly simple version, which is we'll give you a vector of the values in your aggregate, and you can do whatever you want with that. A more sophisticated version would expose like the complete accumulator trait in DataFusion, so being able to allow people to do kind of like incremental updates. That's something we'll probably do at some point. And then, as I mentioned, we just started supporting Python UDFs. So very similar to the REST API, we have a annotation that lets you annotate your function. And behind the scenes, we do a bunch of stuff to make that work with DataFusion, mostly relying on a library called Pyo3 that lets you embed a Python interpreter in your Rust runtime. So that's UDFs in DataFusion. This is a real production system. People are using it every day. And happy to answer any questions. And also later, happy to chat about this stuff. Cool.
Thank you for the great talk. It's awesome. I mean, I'm a little bit out of kind of the data side of ecosystem, kind of an AI side now. So I wonder, who are the typical customers? Can you talk about the use cases? Mm-hmm. What kind of UDFs they actually want, and like where does it actually add value?
Yeah, so I'd say something that surprised us from the very beginning is how many customers wanted UDFs. It was something we implemented from the very beginning, because in our old architecture, which was all ahead of time compiled, it was very easy. And the use cases are pretty broad. A lot of it is like integrating some kind of like third-party library, working around. Sometimes just like functionality we don't provide. It's like the data format parsing stuff is very common. I recently worked with a company that, for some reason, had like their weird own Avro format that was just like Avro with some other stuff appended to it, and a UDF let them, basically ingest that in a sane way. Also, the ad hoc join thing is very common. People want to enrich their data, and they need to be able to like query out to another system. And with UDF, that can actually be pretty efficient because you can kind of embed a cache in the UDF, and so you don't have to like re-query the system every time. And then, calling out to models and inference APIs is also quite common. Yeah, the question is about rate limiting. And actually, yeah, that is built in. So I didn't show this, but when you're defining an async UDF, that UDF annotation, you can also specify a rate limit as part of that.
So this work here is to show the diagram, right? So you basically compile the dynamic library. So what is the life cycle of the workers? Are they per UDF? Are they persistent?
Mm-hmm. Yeah, so the question is about the life cycle of the workers. And the workers, they're persistent throughout the lifetime of the pipeline. So that's what's actually executing the query. So it's pulling from Kafka or whatever. It's executing the logic of the query and eventually producing the result. Often there'll just be one of them for a query, but you can also parallelize. So you can have like horizontal parallelization. And the UDFs are embedded as part of that processing. And generally, for scalar synchronous UDFs, they're just embedded in like a fused function chain. So if you're calling some other SQL function on top of that, it's all just kind of like fused as part of the DataFusion evaluator.
Can you reuse a UDF worker across queries?
So there's no UDF workers. Like the workers are just like the pipeline worker. The UDFs are just like executed as part of the query. So under the hood, there's like a data flow. And within that data flow, there are operators, and those operators may execute expressions. And the UDFs are just like part of that expression that get executed.
So there's a new one
Per query, yeah. And because this is streaming, the queries are like long-lived. So they're often running for hours or days or weeks. Sorry, what was that? Yeah, so great question. Currently, no. For Rust, that generally doesn't buy you that much. We're not copying data at all. when we're just kind of giving you a more convenient API over kind of like the loop you would write anyways. The one exception there is that you could maybe get a little bit more efficiency by producing the results directly, rather than like if you're producing a string, you're going to allocate memory for that string result, and then we're going to write it into the arrow buffer, whereas it would be more efficient just like write it directly. Outside of that case, I think there's generally no performance difference. And like the Rust compiler is going to generally be able to vectorize this for you. For Python, that's not true, though. We definitely would benefit from having a direct arrow API for Python. And I think that will probably be in the next release. Cool. Yeah, thanks so much. And off to the next speaker.
All right. Thank you, Micah. So coming next, we have Luke from Spice AI, reconnecting his laptop. And there's still pizza and drinks if you'd like them.
All right, thanks for having us here. It's great to be here at the Meetup. We're from Seattle, and we're actually hosting the Seattle DataFusion Meetup in October as well, if you're around there. So I was talking to Jeff earlier, and I got inspired because he was talking about the inception of Chroma. And so I went back and found one of these slides, terrible slide deck from our very first raise in January 2021. Well, this was a little bit after that, but the idea was there. About kind of the story about how we got here. But essentially, we were building this neurofeedback system, and neurofeedback is where you take in a bunch of EEG data from your brain, which is a bunch of time series data from electrodes, and you analyze that data and you provide feedback back to the brain, and by doing that, you can steer the brain in certain ways, and so you can put it into different states. And the interesting thing about this problem is that you have gigabytes of time series data, and you have to provide an answer back. You have to analyze the data, provide an answer back to the brain in under 50 milliseconds for it to be accurate. And so it's an interesting problem, essentially, for different types of machine learning. And at the time, we were building this system, and it can essentially reduce the cost of it because you don't have to have a neuroscientist all the time to analyze it. And it was hard with the tool sets that we had at the time. So that's why, so that was one of the reasons why we were inspired to go create this, and one of the problems that we were looking to solve. So before copilots were cool, essentially we had this idea where you could ship alongside your application Copilot that would provide that, you could shove data into it, and it would provide that application, in this case an EEG application, a neurofeedback application, intelligence, and tell it what to make decisions to make and so forth. And so that was kind of the inception of what we're doing here. So this is sorry if it's kind of a cringy slide, but it's from my sales deck. But Luke Kim, before this was 13 years at Microsoft, spent the last couple of years in the C2's office in Azure, built an incubator there called Azure Incubations, built a bunch of other different open source projects, one called Dapper, which is a distributed runtime, but also worked on the infrastructure behind GitHub, with GitHub Actions, a bunch of data platform stuff, and so forth, Visual Studio as well. The problem that we're looking at solving here, one of the problems that we ran into when we started doing this and actually talking to your real customers, is you have this theory about what you want to solve, and then you talk to real customers and then tell you other things. And that was, they were like, well, we're not even at the maturity to implement AI yet because we have this big problem, and there's this big, often a big chasm between where we want to use and consume our data and all the data sources. And organizations, I talked to someone the other day, I had like 150 data sources. Talked to another one, I said, how many data sources do you have? And they said, oh, we have about 30. And then on my next call, they said, oh, we actually counted, and we actually have 150. And they often get these from acquisitions or just teams and so forth. And these can be structured data stores, modern, but also legacy ones, like CSVs on FTP. You would not believe how many organizations I've talked to these days have CSVs and FTPs. and also structured data that you query, and unstructured data, could be documents on SharePoint or so forth. And so there's this big chasm between where you want to consume it and use it and where it lives. And in addition, you also get that chasm often when you want to take that data and provide it into a model. So we heard there's a bunch of these problems all related, right? So disparate legacy data sources, how do I get it? But then once you actually connect all of them, how do I actually make it fast enough for it to be usable? So speed is a problem. And then I can often throw money at it, so then cost is a problem. And then how do I do this reliably when there's data all over the place and access that data? And so then it becomes a reliability problem. And then once you go through that, someone's like, well, hang on a second, you're accessing data from all these places. What about the security and compliance and policy and all of that? And so you have that problem. And so when we actually tried to actually build these intelligent application, decision-making applications, we realized that enterprises didn't just have the problem of how do I actually incorporate this, but all these other problems as well. And in the world, remember, we started in 2021, and ChatGPT came out after that. But then, you also hear this problem often, which is, hey, we went and built this really cool Gen AI thing, and it was a great initial demo, but then we kind of only made it work for this single data source. It didn't have knowledge of everything it needed. It's not secure and compliant. It's not production ready. There's no monitoring observability. And it's definitely not cost effective. And so essentially, we built this, which is Spice OSS. It's a single binary runtime like Aurora and built in Rust, and really acts as a conduit or a runtime to connect your applications, all these data sources, wherever they are, both modern and legacy, structured and unstructured, and your models and AI endpoints. And so if we zoom in, it looks like this. Essentially, it contains 4 building blocks. That orange box in the middle is that single binary runtime. And these are presented over standard database APIs. And the first building block for the Meetup is federated SQL query engine built on DataFusion. We are contributors back to that project as well. And I'll go into detail later in the deck in terms of how we actually use this in this way. But that provides us this access across all of these different data sources in the back end, right? And so now I can join data across, just as easily across Snowflake or Databricks or S3 or CSV files on FTP or GitHub or wherever it lives. And we actually also build in the ability to index and access unstructured data, so I can query files across SharePoint or could be FTP as well, or just a file share, pull those in and use them within the platform as well. But then, of course, how do you make that consistently fast for it actually to be useful? And so we have essentially a data materialization layer, and we do that using an accelerator of your choice. And so you can choose to use DuckDB, you can choose to use SQLite, you can choose to just use Arrow in memory, or an attached Postgres, and with considering other ones in the future, maybe like CHDB. And so now you have data access, and now you have a materialization of some of that data next to or in the runtime, which makes it consistently fast. And then the third building block is ML inference and search. So now can I use some of that data and query over it, access what I need, and provide that into a model. And then the fourth, of course, is can I provide that into an AI gateway? And because all these things are in the same runtime, you now get the ability to hook into the data flows between them. And so now we can automatically start building in monitoring, observability, control, policy, these types of things as you do that. So here's one way of deploying Spice. It's not the only way, but it's pretty common. Because you have a single binary lightweight runtime, often people will deploy it along as a sidecar to their application on the same machine or node. And that provides you this super high performance, low latency access to a materialized set of data right next to your application. And so now you can use that in your application, but you could also use that in inference or with a model or an AI gateway. And then Spice does all the work of managing the data sync in the background. and there's multiple methods of that. We support like an interval on a trigger. We support CDC over Debezium to provide that into the application. Because this is DataFusion Meetup, I'm going to focus mainly on the data side of things and less on the AI side of things. But you can also think, we often think of AI as just another application sometimes that provides, that you need essentially as data foundation. So here's an example that we did with a customer for just data acceleration. Now Databricks here could be anything else, could be S3, could be Snowflake, but they have 100 billion rows in Databricks, a lot of data, and slow queries. And so Spice was a drop-in solution, no change to our application. It was ODBC on a Databricks, ODBC on Spice, and improved that query performance from 15 seconds to 150 milliseconds. And the way it was able to do that essentially is they realized in their application 99% of people only look at the last 7 days of data. And so they configured Spice to essentially prefetch and materialize the last 7 days of data, keep it in DuckDB, which is 10 millions of rows instead of hundreds of billions. And then it provides that back to the application incredibly fast over a local host endpoint. Another use case that we've had is, again, using Databricks. It seems to be a common theme. People like using this with Databricks. But they didn't want to give, this is a security thing, they didn't actually want to give their their internal customers access to Databricks. And so instead of handing out Databricks credentials and so forth, what they were able to do is put Spice in between and essentially provide these mini self-service AI native data warehouses for use case specific or customer specific. So you can actually have one per dashboard or one per application. And you can basically control how many resources you give that to a customer and, or an internal customer and let them go to town and do whatever they want on it, right? You can also just deploy it as a microservice in between. There's a whole bunch of different, a set of microservices or a cluster. And you can do all types of different type of sharding type things here as well, which is pretty common. We also support catalogs, so you can connect across to a catalog and use that to define your data sets. And you can actually chain these things, so you can have a spice-to-spice instance to push down data. So with that, I'm going to speed run through that. I'll just get to some live demos. So the first demo I'll give is a very basic one, and this is all on my laptop. Essentially, how do we just access data on S3 and make that fast? So swap across to here. So here we have just a blank project. Now, what I learned from working on these projects for a long time is you want to make these things as developer friendly as possible. So we essentially have a CLI that's very easy to get, one command line, and we wanted to make this in a similar experience to like something like pip or npm. And so we have a package manager behind the scenes, and so I can do spice add spice AI quick start, and that's going to go to the registry, pull down this manifest file, which looks like this, and it doubles as a CRD in Kubernetes, but essentially provides a config with a dependency called spice quick start, and I can go across that quick start, and you'll see it's very basic. It's a datasets, and really just gives a pointer over to an S3 bucket. We're going to call this taxi trips. The file format is Parquet, and then I have this acceleration thing, which I'm just going to turn off for now. So again, just a single binary you can run on your laptop. I'm going to do spice run, and that's going to start the runtime. And it's going to use that config file, and it will go across to S3, pull that Parquet file down, or sorry, in this case, just connect to that Parquet file and make it available for query. So if I open up another console here, then I can do, we have a little REPL command on our CLI called SpiceSQL. If you've used DuckDB, it's similar. And now, or even the DataFusion CLI, so I can do show tables. And you'll see now I have the taxi trips table there that I configured in that YAML file. And so now I can just query on that. So select star from taxi trips, where, or I just say limit 100. And what that's doing is connecting to the runtime, executing that query, going to that Parquet file to S3, doing the query, and you can see it is a little slow. which is good. It should, sometimes this depends on the network, but. Okay. I'll let it finish. Okay. Interesting. Well, okay. So I just built before, which was probably a bad idea. I'm just going to reinstall it and do this live. The great thing about live demos. All right, so now I got Spice version. I've got the latest version here. And hold on, I'm just going to do some great force. Nope, that's not what I wanted to do. Let me just see if this will run. This is not, yeah, I'm surprised that I got this. All right. Well, if that's not going to work, then I will move on. But let me at least explain what I was attempting to show you there. Obviously, I could just query, get the data, and then what I would have shown you is turning this on to acceleration true. And then what it would do in the background essentially is prefetch that data, make it available in the runtime, and then I would be querying on a local replica of that data, which would make it incredibly fast. And I can also configure this to be, say, DuckDB as an engine. I could be SQLite as an engine here, or Postgres as an engine as well. So good thing I have another demo, and we'll get to that. All right, so what I hopefully would have shown you, if it would have worked, is that it was super simple to set up. It was just this config file that I could get, and it actually makes it highly available because you can essentially keep this replica of data in DuckDB on the machine, and hopefully it would have shown you that it was very, very fast, but I can show you in our cloud platform. So here's the next demo on how to wire it up, and this is a little bit more complicated. And so one of the benefits we saw is like how in an enterprise do you access data wherever it lives? And then how do you eventually provide that into a model? And so here we have Databricks, Postgres, GitHub, GraphQL, and FTP. And we're essentially going to build a GPT around the open source project called Nginx. And so you don't need to know too much about the projects. It's a proxy, but we're essentially getting data around that project that we can provide. So I'm going to swap over to my browser here, and this is just our interface for Spice, the cloud platform. I'm going to make that bigger so you can see. And then we have that same spicepod.yaml, which is that manifest file that I showed you before. And this one's got a little bit more stuff in it, but you can see here that I've got a data set instead of S3. It's actually connected across to Databricks, and calling that, getting the security advisories for the project. Here's a little bit of more information to help the, to give hints to the AI. We also have S3 here as well. These are CSV files in S3. We have FTP source here, and these are markdown files. And then we have GitHub here, and we're pulling commits from that. Now, in addition, we have the ability to specify these embeddings, and so, or essentially embedding providers. And so here, we can just say use the OpenAI embedding API. And here we can say pull down a model from Hugging Face and use that for embeddings. And in addition, we want to be able to specify the AI providers. And so here we've just said use OpenAI, use GPT-4, and here's some system prompt stuff. But this could also be, any other different variations of this. Here we're actually using Grok in the bottom here as well. And so that's the full configuration file: 4 data sets, 2 embeddings, 2 embedding models, and a bunch of AI endpoints at the end. And so in our hosted version, it's just hosting one of these instances in the background. But this is all completely self-hostable. You can run it in your infrastructure. You don't need to use the cloud platform. So here we have I can just also show tables again, and we have those 4 tables here, and these come up on our dataset reference here. And so I can just say, here's the CVEs, and these are actually very fast, so everything is sub-second on the query. I can take a look at commits here. This is select star count from commits, and I think there's about 8,000 commits here. And so essentially now you have this ability. Remember, I had Databricks, I had FTP, I had GitHub, and so I can actually do joins across this data because it's all materialized very quick, very fast in the actual runtime. And when I say materialized, that could also just be stored, could be a DuckDB file stored on an attached NVMe drive. And so you can store terabytes and terabytes in this materialization. But how might we actually access that data really fast from this model? So here we have, again, the same configuration that I put in the configuration of each of those endpoints. We just have a bunch of them here. Here's one without Spice. And so I might say, hey, what is Apache DataFusion? You can just see this is just a standard chat interface. Hopefully it doesn't go too long. But what I might say is, what data sets do I have access to? And because it's just using the standard OpenAI model, it just gives me a very generic answer. But now if I was to select the OpenAI with Spice, what Spice will do, remember you had those 4 building blocks in the same runtime, is do all the work of actually accessing those data sets, understanding the schema, packing all that in context, packing that into the prompt so that the model understands those data sets. And so now I could say, what data sets do I have access to? And with no code on behalf of the user, just that configuration file, it can wire up the 2. And so now you can see I've got access to those 4 data sets that I had configured. And so I might want to say something like, and now I can just query that. So I can say what CVEs were related to the quick protocol, something like that. And it's a little slow. And so it's able to query across that data and then provide the experience without any additional work on behalf of the user into the model here. And then we have citations and so forth back to the references and so forth. So this is all real data. And because this is the query engines built into the same runtime, it can use that to actually query data. So I might say, who were the top committers to the Nginx project? Use SQL to get actual commit numbers. I should say. And so now it can actually use that SQL query engine because it's all in the same runtime to actually just go get that data. And remember, that's data access across all of these different disparate data sources, and they could be modern or legacy. Now, because you want to actually deploy this to production in a real enterprise, you don't just want that. You actually want to know everything that's happening behind the scenes. And because you could hook into those data flows between them, then you have monitoring every SQL query, every completion, every vector search. But even beyond that, what we have is the ability to fully trace everything that happens in the system. And so here, if I was to look at it, I'd say what CVEs were related to the quick protocol, then I can see all the inputs and outputs to the system, and then I can see the full trace of everything that happened. And so here's the text embed, here's the vector search. But if I was to go back to the second one here, and I will say who were the top committers to the project, you can see that it's able to go get the table schema. And by the way, this is incredibly fast, 0.086 milliseconds, because it's all within the same runtime based on Apache DataFusion. And so here is the actual text to SQL, and here's the actual SQL that I executed, and these were the counts that you saw and come up in the chat there. And I can go and, of course, just run that within the platform, debug it, and so forth within the thing. Now, one of the benefits of having this all within one runtime is that it can try and get feedback very fast. So, for example, if it generates SQL that's not valid, it immediately has DataFusion there as a SQL parser to tell it that it got it wrong. So there's no round trip back to like some external database system just to know that the SQL you got was wrong, right? And so now you can even start doing really interesting things with it, like for example, when it got it wrong, take the explain, or when it was too slow, take the explain, feed that back into the LLM, and then have that really optimize the query across these systems in the backend. That hopefully just shows the power of combining DataFusion with the actual inference and AI gateway. So as I mentioned, the idea is to provide you with an actual deployable production grade system here for monitoring observability. You can deploy those models from Hugging Face, so it can all be local as well, but you also want all of that enterprise grade control and policy that goes along with it. So how does all this work? I wanted to kind of dive into a little bit of the actual DataFusion behind the scenes, how we actually wired all this up. So first, I just wanted to talk about, we made a series of design decisions, technology bets for the runtime. And so this is all built on an open source foundation, Apache Arrow from the very beginning, Flight, DataFusion, Parquet, Iceberg, these technologies. The runtime itself is Apache 2.0 licensed. And then our model is to really give users the choice of the best-in-class thing that they want to use for their use case. So you can use OLAP accelerator here. You can use OLTP accelerator, SQLite or Postgres. And then we have key value on the roadmap. And the idea, again, is just to provide super high performance data access into your application or models. And then really developer-friendly experience. There's two major projects in DataFusion that we're really involved in. One is DataFusion Federation, and I'll talk a little bit about how that helps us. But that really provides the way to access all of these different disparate data sources. And two, DataFusion Table Providers, which is a repo that we contributed back to the project, which gives you the ability to translate these basically query plans into SQL that you can call into other backend data providers. So to zoom in a little bit on the federation, what happens here is, imagine I wanted to do a SQL query to join multiple different backend databases. So that could be, in this case, DuckDB and Postgres. And so you'll get a query that comes in, and then using the DataFusion Federation project, it looks for the biggest subtree that can fit within each one of the nodes. And then it essentially turns that into a federated node, and then it uses what's called the unparser to take the logical plan, unparse it back into SQL in the dialect of that backend store. So it's going to convert that into the dialect for DuckDB or into Postgres or into MySQL, and then push those queries all the way down into the backend databases here. And so that allows you to push as much compute into the backend databases. And if you don't have that, what you essentially have to do is a full table scan in each, bring it all the way up and say do a join within DataFusion itself, which is, can be very, very slow. And you need this even just within the same runtime. So for example, you can actually choose to have multiple accelerators. So maybe I would have SQLite, some tables in SQLite, some tables in DuckDB, and what I can actually do is push the joins down to even both of those, even just within the runtime, not even within having to do this outside into another system, which is very valuable. And Philip created these slides, so I kind of wanted to credit him there. He's my co-founder and CTO. Thanks, Philip. The next problem that you have when you do this is we have used Arrow as a substrate for everything that we do. And so that's normally pretty good when you have other columnar data stores or formats, but what happens when you have rows? And so we have to do a bunch of Arrow to row conversion and row back to Arrow for these stores. Normally when Arrow to row, it's pretty simple. We can just essentially do a conversion and put it into the dialect. But when you go back the other way, it becomes more complicated because you essentially get types back. Say I'm querying Postgres, I'm getting a bunch of rows, and I get these Postgres types back. I've now got to convert every single one of them back into arrow types and then put that back into a columnar store. And so we've done a bunch of work in DataFusion itself to actually do that, all the conversions back and forth. And then, in addition, we have to make this really fast, we also put a results cache in front of it. And this is interesting in terms of DataFusion because we actually decided to make the cache key the logical plan. And so what you can actually do then is if someone did like a slightly different SQL, but it essentially compiles down to the same plan, you still get the same cache result back, right? And so it'll come into the execution engine. It will try and get it from cache. If it's a miss, then we build the essentially key from the logical plan. And then we have this acceleration feature, which will essentially you'll be able to serve it directly from the cache, and if you miss, it'll run the query on the accelerated table, and then if it's not there, you also have the option to actually go back into the fully underlying data store as well. And so all of this makes it incredibly fast. And then the final thing that I wanted to just dive into is how we do some of the embeddings. The guys asked me about this before. And so again, our model is not that we're going to be the best of all these things, but we want to help you compose the best-in-class things that you want to choose and use together. And so if you wanted to use pgvector, you can use that. If you want to use a DuckDB vector extension, you can use that. And we'll wire it up together. And essentially, what it allows you to do is take in data from any of these stores, choose a column, calculate an embedding on that, and then we will pull it into the table. And then on the acceleration side, you can keep that embedding stored in the acceleration for very fast lookup here. And so essentially what it allows you to do is calculate these embeddings across all of these other stores, keep it all in one place, keep it very, very fast for very, very fast search and lookup, and you still get to have your own choice of how you actually calculated that. What I forgot to show in the demo here is, if I come back to the configuration real quick, is just how you wire this up. So here we have an embedding model here from Hugging Face that we've pulled down. And so you might want to do that if you want to keep everything sovereign within your infrastructure. And then here we have commits. And so the way you wire it up is super simple. All you say is, hey, with these 4 lines of code, on the column message, use the Hugging Face model we just pulled down to calculate embeddings. And then we also say, here's a primary key. And the interesting thing about the primary key is that once I do the similarity search and I find essentially the row, then I can use the primary key to actually fetch data around that because I have the query engine directly there. And so you now start getting this interesting aspect of data access combined with search, where you can search, find something, but then say query all the surrounding rows around it in the database very, very fast because you have that data directly there. Or more columns, you want to bring in more columns that you might not ordinarily have. So that way you can actually make it a whole lot more accurate. So yeah, with that, it was a pretty fast dive in to the details, but kind of what's next for us here, we're going to add in a bunch of additional auth-C, auth-N security things. We also support catalogs to do things like credential vendoring, so you can get temporary access to this data and make it all safe. And then have a bunch of policy and guard layers as well here. So you can essentially combine multiple models to do this. You can see where you define multiple models there. And then we also have the ability to control it with remote configuration and essentially being able to make a data firewall between your data sources and your models in your application, right? So yeah, we have an open source project, like I mentioned, for very high performance data access and then RAG and AI. And it can also provide this high resiliency because you have this local replicas of data with it. We don't have nearly as many stars as Chrome, so would appreciate if you give us a star. And then we also have a cloud platform for hosting and an enterprise version of this as well. So I know it was pretty long, but thanks for bearing with me, even across the demo. And yeah, hopefully that you learned something about federation and acceleration in DataFusion.
thank you very much. Great overview. When you showed OpenAI Spice model, is the GPT using OpenAI GPTs? You trained, how did you build that?
Yeah, so that's just using standard OpenAI GPT model. It could just as easily be a local model. It could have been Grok, it could be Anthropic. But Spice in the runtime did all the work of feeding all the data into it. So literally everything you showed there worked without any code. There was no code. It was literally that configuration file there. And the other thing is we present the runtime APIs over standard OpenAI APIs. So you can actually just point the OpenAI SDK or the Vercel AI SDK. We also have a Vercel AI SDK provider at the runtime, and it just looks like OpenAI. And so you can start composing these things together. So you have a standard database APIs, standard AI APIs.
Can you use Llama instead?
Yes, you can. Yeah. You could just as easily use Llama. Yeah. All right. Well, thank you.
All right. Up next, we're going to have Amay from Denormalized. But beforehand, we're going to let Jeff from Chroma say a couple words since he's hosting. So thank you.
Cool. Almost had a feedback error there. Awesome. Well, I don't really have a script or a narrative, but it's great to see you all here. Thanks for coming to our office. Chroma is an open source vector database. Yes, we do have a good number of stars, though we also can use more stars. If you want to stars Chroma's repo as well, we welcome it. And yeah, we're really passionate about Rust. We've been running a lot of Rust as a team, and I think we're early on our DataFusion journey here, but I think we're learning a ton tonight. So thanks for coming.
I think we have the fewest stars because we're the newest. So, if you want to root for the underdog, but
Let's keep a start with everyone.
I think presenter. Okay, cool. So my name is Amay. I'm co-founder of Denormalized along with Matt, and we are building an embedded stream processing engine on top of DataFusion. Although tonight's talk would be more about how do you build, a extension to DataFusion, right? I think one of the first things when Matt and I were exploring ideas was I told him, Matt, stop me if I were to propose building a database, and because historically that has been a very foolhardy venture, right? And DataFusion is it's a hard thing to describe because I was at Kafka Summit last week, and I saw people building durable execution engines use DataFusion for SQL stuff to their journaling. So you can think of DataFusion as a DuckDB competitor, in a way that you can just run SQL. But it's actually much more than that. It's really a Swiss Army knife in a way to create to build databases or extend your database capabilities. For instance, I think the Spice AI guys, you guys use the SQL parsing capabilities of DataFusion quite a bit to do transpilation between different engines, which is very cool. So yeah, so how do you build your own database on top of DataFusion? So yeah, I'm gonna present a little case study. So yeah, so databases are some of the most complicated pieces of software written, especially the system software, but they're actually not that complicated. You can basically decompose databases to, what do they have? They have a front end, SQL and data frame. Those are the two types of popular front ends. Then you have some sort of an optimization phase. You typically have the front ends, they transpile to a logical plan, then you have multiple logical optimizers. So and then these logical optimizer, will convert the logical plan and finally give you a physical plan, which in DataFusion is called an execution plan, which also goes through physical optimization phase. So you can, one of the questions might be what's the difference between logical optimization and a physical optimization? Logical optimizations are typically you have a select star, but you're only using a couple of columns later down in your aggregate. So a logical optimizer will figure out that you don't actually need all those projections in your plan, and that will actually, at the scan level, optimize that. So that's a very, it's on a logical level. While a physical plan is actually aware of the actual execution environment of your system. So depending whether you're building a distributed database with shuffles and checkpointing, or you're building a single node system, you will have different considerations. And finally, the physical plan, which is again a compute graph, gets shipped over to the execution engine, which in DataFusion is really built atop Tokio, and each of the operators runs as a series of parallel tasks known as streams. So how does one write a custom physical operator in DataFusion? So since we're building a single node stream processing system, streaming systems typically do things like windowed aggregations. A stream typically you want to give it some bound. I want to compute aggregates over 5 seconds on the stream of data that's coming in. So let's try and write something like that. So how do we write a custom physical operator in DataFusion? They're called execution plans. They represent the physical operator. Each physical operator has a method known as execute, which produces a synchronous sendable record batch stream, which you can really think of as a asynchronous stream of record batches. And these physical operators also, when you're designing your own, you can specify different things such as the partitioning requirements. You can specify the input partitioning and the output partitioning, as well as a few other things such as the execution mode of that operator. So execute is the method that you would want to implement. That's like the one that every physical operator needs to have. And as you can see, it's really a record batch stream, so you have to implement a stream poll loop in DataFusion. So for implementing our windowed operator, how would that stream poll loop look like, right? So for instance, this is like how every DataFusion physical operator looks like. You have a record batch stream, which is really a special case of a stream, which is a concept from futures in Rust, and you have to implement the poll loop. So typically your logic would go inside this helper method that we're delegating to called poll next inner. So all that this method does is every time there is data, because you can imagine you're a physical operator, you're somewhere in the graph, you're waiting on data from your upstream nodes. So every time you get data, you have to specify what to do with that data actually. I'm not going to bore you with another wall of Rust code, but our streaming window operator, what it needs to do is process incoming data, accumulate rows into open windows, update watermarking, because in streams you need to figure out where, how far the stream has reached. You have to open new windows especially if you have some window trigger condition, and you have to close any triggering windows which produce output. So typically you can think of a windowed aggregation in streaming systems as you're batching data for some time. Typically it's like 5 seconds for what have you, and then you want to every time the watermark moves by that 5-second mark, you actually want to run the aggregate on the data that you accumulated by then and produce the output. So that was our physical operator, but how does this actually tie in to the DataFusion runtime? So like we mentioned, right? Database internals, you typically have a logical plan node that corresponds to the physical plan. So what we have done is we have created the execution operator, but we also need to create a logical plan node and a companion physical planner. In DataFusion, it's known as extension planner, which is what the query planner uses. So let's see what a logical plan node looks like. It's actually a fairly uninteresting trait that you need to implement, but the most interesting method here is a logical plan node needs to define what to do every time any of its any of its expressions or the upstream inputs get changed, right? So imagine a logical plans node is just to represent the computation without physically caring about how that computation happens, but a logical plan gets optimized multiple times through the optimizer pipeline, so the graph changes dynamically in this process, so your operator needs to account for that. So a very typical thing that happens is that the optimizer figures out some of your expressions are perhaps not as efficient, and it will perhaps make them more efficient. So if your operator depends on some arrangement of the expressions, it needs to be able to self-update if the logical optimizer updates those expressions. And once you have the logical plan node that you have built for your new operator, you can just in your front end, you can just register that as a logical plan extension. This hooks in with DataFusion's logical plan pretty nicely. All right, so we also need to hook into the physical planner. We need to create something called an extension planner and by the way, I didn't come up with all these names and concepts. They tend to jump all over the place, if that is my criticism of DataFusion. But so the extension planner here is the physical planner version of the logical node. What an extension planner here basically does is when I'm creating my physical plan, and this plan is created recursively, is essentially it's a tree structure. So whenever a physical operator is being created, all we have access to is the tree up until that point. So you have to figure out, based on the state of the tree, what type of physical operator that you have customly designed to return. Typically, there isn't much to do here. You essentially just want to plug in the execution plan that you created here. So that is the extension planner piece of it, and then you also need to then so we have the logical planner and the physical planner side of it. Now we actually need to hook them up together so that given a particular logical plan, how do I return a physical plan which contains the new operator that we created? You need to implement a trait called query planner, which is actually fairly straightforward. As you can see, we are basically extending. We are basically extending the available physical plans with the new physical planner that we created in the previous slide. So I know this sounds a bit all over the place for so far, and is that it all? No, perhaps you also might need to write your own optimizer rules. For instance, what we just created was a streaming aggregation window, and we want to add an optimizer rule that every time there's a group by, make sure that the partitions have keys have all the keys in the same partition, especially the keys that are in the group by. So for instance, then we need to write our own rule. So this rule I call ensure hash partition on group by for streaming aggregates. So here we can, this is an optimizer rule that adds another physical step if it detects that there's a group by, to make sure that you add a partition operator right before you add our window operator. So how do these all disparate things we built wire together? It's actually simple in DataFusion. Through this process, we built our new query planner. So in the DataFusion session state, you can actually specify the new query planner you created. You can also add the new optimizer rules you created. So that is all there is to it. This is all it really takes to really extend any database with whatever new use cases and operators you want. And DataFusion is a fairly, it has table providers for different catalogs now. So you don't really need to write 95% of the things that are involved in writing a database. So you can then focus on the specific use cases you care about and still get still get rest of it for free. That said, there are some things to watch out for. DataFusion APIs are in a state of flux, and we have all been burnt by how often they're rewritten. So that's always a challenge. They will break your database, so to speak, with each version. The Python DataFusion and DataFusion Core are not always in sync, so if you're relying on that as a part of the functionality you offer, something you need to watch out for. Another thing is optimizer rules have been created. We have figured them out over like 30, 40 years of database research. That said, it's very easy to write operators that, the optimizer rules will break them. Typically, especially if your operator involves adding another column in the middle of a pass, typically, right? Like if you want to look up a new value by making a web call, that's a column that got created midway in the operator. And the way SQL databases think is that all the projections always start at the scan time. So, it's very easy to do that. So that said, it's not really that hard. You can just turn off some optimizer rules, but that's really about it. And I will attempt another live demo. So hopefully this goes better. So let me stop this. Okay. All right, so yeah, I just want to demonstrate the streaming window aggregator that we never mind, I lost my... All right, I did miss one slide. That slide was going to show the job we were running, but so what we're running is actually, you know what? I think it's worth it for me to try and recover that. So I have to log into Figma again. Yes, so let me... So let us demo the operator that we built. So this is a new operator. I guess there is a window operator in SQL. This is a streaming window, but that's a minor point. We're gonna window on a stream over a Kafka topic that where we are grouping by the sensor name. So this is a stream from like classic IoT data that's being read, and we want to do some sorts of counts, min, max, average type accumulations on that stream, and we want to window them by 1 second each. And so we have 1 second windows grouped by sensor names, and we have a bunch of aggregates such as count, min, max, average. As you can see, this is sort of how the resulting physical plan looks like. The streaming window exec is the operator that we wrote. That is the custom one. And as you can see, we also wrote the optimizer rule that always partitioned by the group by expression. So yeah, and it showed up in the physical optimizer. It showed up in the physical plan itself. And now I can, let me run a quick job to emit to my Kafka, and I will run the simple aggregation that I described. As you can see, this is a live aggregation. It's running 1 second windows grouped by the different sensor names. So yeah, that was that. So yes, this presentation was 15 minutes. So ideally, that's how long it should take you to write your own operators in DataFusion. But yeah, cool. That's what my presentation is.